Have you ever gazed at the night sky and pondered the sheer scale of the cosmos? Beyond the serene twinkle of distant stars lies a universe of dynamic forces, where celestial bodies are in constant motion, sometimes on a collision course. Today, we embark on a scientific journey to explore the profound reality of cosmic impacts, from historical airbursts to hypothetical planetary collisions, dissecting the physics and geological consequences that shape worlds. This isn't just science fiction. It's a deep dive into the astronomical phenomena that have sculpted our planet and continue to define its cosmic narrative. On June 30th, 1908, at precisely 7:17 a.m. local time, an unprecedented atmospheric event unfolded over the Podkamennaya Tunguska River in Siberia. This was no ordinary explosion. It was a cosmic encounter, a stark reminder of Earth's vulnerability to extraterrestrial objects. The Tunguska event, as it became known, remains one of the most significant impact events in recorded human history, offering invaluable insights into the mechanics of bolide airbursts. Scientific analysis suggests a stony asteroid or cometary fragment, approximately 50-60 meters in diameter, entered Earth's atmosphere at an estimated velocity of 15 kilometers per second, 34,000 miles per hour. Instead of striking the ground, this extraterrestrial projectile detonated at an altitude of 5 to 10 kilometers. The resulting airburst released an astonishing 10-15 megatons of kinetic energy, equivalent to over 1,000 times the destructive power of the Hiroshima atomic bomb. The immediate aftermath was catastrophic. The superheated plasma generated by the explosion created a powerful shockwave that flattened an estimated 80 million trees across an area exceeding 2,000 square kilometers. Eyewitness accounts from hundreds of kilometers away reported blinding flashes, intense heat, and seismic tremors. Remarkably, due to the remote location, no direct human fatalities were officially recorded, though the event left an indelible mark on the scientific community and fueled decades of research into impact physics and planetary defense. Perhaps the most famous and scientifically validated cosmic impact is the one that occurred approximately 66 million years ago, marking the boundary between the Cretaceous and Paleogene periods. This cataclysmic event, known as the Kapege extinction, irrevocably altered the course of life on Earth, culminating in the demise of the non-avian dinosaurs and countless other species. The evidence for this impact is compelling and multifaceted, a testament to rigorous scientific inquiry. Geological strata worldwide reveal a distinctive layer of iridium, a rare element on Earth's surface but abundant in asteroids. This iridium anomaly, coupled with the discovery of the 180-kilometer-wide Chicxulub crater beneath the Yucatan Peninsula, provides irrefutable proof of a massive extraterrestrial impactor. The asteroid, estimated to be 10-15 kilometers in diameter, struck Earth with unimaginable force, releasing energy equivalent to billions of atomic bombs. The immediate consequences were apocalyptic. The impact generated colossal tsunamis, global wildfires ignited by superheated ejecta, and a massive release of sulfur aerosols into the atmosphere. This led to an impact winter, where sunlight was blocked for years, causing a drastic drop in global temperatures and widespread cessation of photosynthesis. The subsequent collapse of food chains, coupled with ocean acidification, created an environmental cascade that led to the extinction of approximately 75% of all species on Earth, paving the way for the diversification of mammals. While the Tunguska and Kapege events offer empirical data, planetary science also delves into hypothetical scenarios to understand the extreme limits of cosmic dynamics. What if a body of planetary scale were to collide with Earth? Let's consider two extreme, albeit highly improbable, scenarios involving our celestial neighbors, Mars and Venus. These thought experiments illuminate the immense forces at play in the early solar system and the potential for planetary accretion and destruction. Imagine Mars, a planet roughly half the diameter of Earth but with about 10% of its mass, suddenly perturbed from its stable orbit and set on a collision course with our world. As Mars approached, the mutual gravitational attraction would intensify dramatically. Tidal forces would begin to distort both planets, triggering massive seismic activity and volcanic eruptions on Earth. The red planet would loom ever larger in our sky, its gravitational pull generating colossal tsunamis that would scour coastal regions and reshape continents. Upon impact, the kinetic energy released would be staggering, far exceeding anything in human comprehension. The collision would not be a simple splat, but a violent, multi-stage process. The initial shockwave would propagate through both planetary bodies, vaporizing vast quantities of rock and metal. Earth's crust would be fractured and partially ejected into space, while Mars would be utterly fragmented. The resulting debris field, a superheated plasma of silicate and metallic vapor, would envelop the remaining planetary cores. The aftermath would be a molten, unrecognizable protoplanet, its surface a churning ocean of magma. The atmosphere would be stripped away, replaced by a superheated cloud of vaporized rock. While Earth's core might remain largely intact, the surface and mantle would be utterly transformed, a testament to the destructive power of planetary-scale impacts. Life, as we know it, would be instantaneously extinguished, leaving behind a world reborn in fire. Now, consider Venus, Earth's sister planet, with a diameter nearly identical to ours and over 80% of Earth's mass. A collision with Venus would represent an even more catastrophic event. A true planetary annihilation. The combined kinetic energy of two such massive bodies colliding at cosmic velocities would be unfathomable, leading to the complete disruption of both planets. The impact would generate an explosion of such magnitude that both Earth and Venus would be torn apart, their constituent materials vaporized and scattered across a vast region of space. We wouldn't just become massive, fiery fragments. We would cease to exist as distinct planetary bodies. The energy released would be sufficient to overcome the gravitational binding energy of both planets, transforming them into a colossal, superheated debris disk orbiting the Sun. Over astronomical timescales, however, the laws of physics dictate that this debris would not simply dissipate. Through a process known as accretion, gravitational forces would gradually draw the scattered material back together. This reaccretion would eventually form a new, larger planetary body, a hybrid world composed of the mingled remnants of Earth and Venus. This new planet would be a testament to the cyclical nature of cosmic creation and destruction, a world utterly devoid of its original life forms, a stark, molten sphere slowly cooling over eons. While the Mars and Venus scenarios are hypothetical, the scientific consensus for the formation of our Moon provides compelling evidence that planetary-scale collisions are not only possible, but have fundamentally shaped our solar system. The prevailing giant impact hypothesis posits that approximately 4.5 billion years ago, early in Earth's history, a Mars-sized protoplanet, often referred to as Theia, collided with the nascent Earth. This colossal impact was not a direct head-on collision but a glancing blow, which explains several key observations. The impact ejected vast quantities of Earth's mantle material, along with fragments of Theia, into orbit around our planet. This debris then rapidly coalesced through gravitational accretion to form the Moon. Scientific evidence supporting this hypothesis includes the Moon's relatively low density, suggesting a lack of a large iron core, its orbital characteristics, and, crucially, the isotopic similarities between lunar and terrestrial rocks, indicating a shared origin. Today, The probability of another major planetary collision involving Earth is astronomically low. The orbits of the planets in our solar system are remarkably stable, governed by precise gravitational dynamics. While Venus is approximately 40 million kilometers away, and Mars no less than 56 million kilometers at their closest approaches, these distances, combined with their orbital mechanics, ensure a safe cosmic dance. Scientists estimate the probability of a Mars-Earth collision within the next 4 billion years to be less than 1%. This statistical improbability offers a reassuring perspective, allowing us to appreciate the dynamic history of our solar system from a position of relative safety. From the localized devastation of Tunguska to the global cataclysm of the KPG extinction and the theoretical grandeur of planetary mergers, cosmic impacts are a fundamental force in the universe. They remind us of the dynamic, often violent processes that govern celestial mechanics and planetary evolution. Our scientific understanding, built on meticulous observation, data analysis, and theoretical modeling, allows us to reconstruct past events and predict future possibilities, however remote. If you're fascinated by the intricate dance of celestial bodies and the profound forces that shape our universe, then join our scientific community. Subscribe to our channel for more deep dives into astrophysics, planetary science, and the mysteries of the cosmos. Hit the notification bell so you don't miss our next exploration, and share your thoughts on these cosmic phenomena in the comments below. Let's continue to unravel the universe's secrets together.
Don't forget to subscribe to our channel and support the videos. I wish you to be healthier.